Hi there, welcome to Ancient Cosmos Sleep. Tonight we leave behind the familiar glow of Earth and drift into a realm so vast that even entire galaxies seem like scattered lanterns in a distant fog. You float through darkness that is not truly empty, but woven with ancient light, invisible matter, and stories that began before human civilization learned to write its first symbols. Ahead of you hangs a giant among giants, a galaxy known as Messier 87, a colossal island of stars resting deep within the Virgo cluster. At first it appears peaceful, almost serene. A soft golden glow spreads through space like a cosmic candle flame. Yet hidden within that calm radiance lies one of the most extreme objects ever discovered. Deep in its heart lurks a black hole so massive that trying to imagine it is a little like trying to count every grain of sand on 1,000 beaches while half asleep. And here's your bedtime reality check. If you somehow wandered too close to the center of M87 without advanced technology, you probably wouldn't survive the experience. In fact, probably is being surprisingly optimistic. So, before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And while you're settling in, feel free to share your location and local time in the comments. It's always fascinating to see where in the world fellow travelers are listening from. Now, dim the lights. Maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You drift farther outward from Earth, watching the familiar stars of the Milky Way slowly shrink behind you. Distances begin losing their meaning. Millions of light years pass beneath you like milestones on an endless road. Eventually, you enter the territory of the Virgo cluster, a vast gathering of galaxies bound together by gravity. This is not a small neighborhood. Thousands of galaxies occupy this region, each containing billions or even trillions of stars. Near the cluster's center stands Messier 87. Calling it large feels almost unfairly modest. M87 is a giant elliptical galaxy, one of the largest galaxies in our cosmic neighborhood. While your own Milky Way contains perhaps a few 100 billion stars, M87 may contain several trillion. Looking at it from afar is like comparing a modest town to a sprawling continent. The galaxy glows with a warm golden color because many of its stars are old. Their light has been traveling through space long before the first humans looked up and wondered what those tiny points overhead might be. One mainstream historical fact about M87 is that it was catalogued in 1781 by the French astronomer Charles Messier. Messier was actually searching for comets. To avoid confusing permanent fuzzy objects with moving comets, he created a catalogue of troublesome deep sky objects. M87 became entry number 87 on that list. Imagine accidentally creating one of astronomy's most famous catalogues because you were trying not to be distracted. That is the scientific equivalent of organizing your desk and accidentally discovering a treasure map. As you approach the galaxy, its shape becomes clearer. Unlike spiral galaxies with elegant arms, M87 appears smooth and rounded. It resembles a vast, glowing football of stars suspended in darkness. No obvious spiral structure emerges. No dramatic pinwheel pattern spins across its face. Instead, stars swarm through enormous volumes of space in countless overlapping orbits. The galaxy feels ancient. And in many ways, it is. Astronomers believe giant elliptical galaxies often form through repeated mergers. Over billions of years, smaller galaxies collide, merge, and blend together. Their structures become scrambled. Spiral arms disappear, new stars form, old stars settle into complicated orbits. M87 may represent the result of countless such encounters. You can imagine cosmic history layered within it, like rings inside an ancient tree. A strange and quirky tidbit, often mentioned by astronomers, is the enormous number of globular clusters surrounding M87. The Milky Way possesses roughly 150 known globular clusters. M87 hosts thousands upon thousands of them. Picture dense spherical swarms containing hundreds of thousands of stars each. Then imagine thousands of those swarms orbiting one galaxy. It almost feels excessive, like someone decorating a cake and deciding that one cherry was not enough, then adding 10,000 more. As you continue floating closer, the scale becomes difficult to comprehend. Light itself requires years to cross relatively small portions of the galaxy. Individual stars remain separated by unimaginable distances. Yet gravity quietly binds everything together. The universe often behaves this way. Its greatest structures are built not through violence alone, but through patient persistence. Tiny gravitational pulls, repeated across billions of years, create objects so large that human language struggles to describe them. The Virgo cluster around you stretches in every direction. Galaxies drift through the darkness like luminous islands. Some interact, some collide. Some quietly orbit the cluster's center. M87 dominates much of this environment. Its immense mass influences neighboring galaxies and contributes to the cluster's gravitational architecture. Astronomers studying the cluster discovered that visible matter alone cannot explain all observed motions. This realization became part of the larger story leading to the concept of dark matter, the mysterious substance thought to make up much of the universe's mass. You cannot see dark matter. No telescope directly photographs it, yet its gravitational fingerprints appear everywhere. Like a cosmic cat walking across a table while remaining completely invisible, it leaves clues without revealing itself. As your journey continues, attention slowly shifts toward the galaxy's center. The outer regions glow peacefully enough. But something unusual resides within. Stars near the core move in ways suggesting tremendous gravity. Gas behaves strangely. Energy emerges from the central region with astonishing power. For generations, astronomers suspected that a gigantic object occupied the heart of M87, yet proving its existence would take decades. And even after evidence accumulated, questions remained. Historians still argue whether certain early interpretations of active galactic nuclei delayed or accelerated acceptance of supermassive black holes as real physical objects. Scientific progress is rarely a straight road. Competing theories often coexist for years before evidence gradually tips the balance. Back in the 19th century, no one looking through a telescope could have imagined the true nature of M87's core. Even in the 20th century, certainty remained elusive. The galaxy seemed calm from a distance, elegant, ancient, almost sleepy. But hidden beneath that tranquil appearance was a gravitational engine, unlike anything humanity had ever encountered. The clues were already there, waiting patiently inside the light. And as you drift deeper toward the glowing center, you begin to sense that the story of M87 is not merely the story of a galaxy. It is the story of how human curiosity slowly learned to see the invisible. A story that will eventually lead to a photograph once considered impossible. A story involving continents, radio telescopes, atomic clocks, and one shadow cast by a monster so immense that space itself bends around it. For now, though you simply float in silence beside this ancient giant, letting its golden glow surround you while the mysteries of its heart remain hidden just beyond sight. The darkness ahead grows deeper. The journey continues. The golden glow of Messier 87 remains beside you as you continue drifting through the Virgo cluster. From this vantage point, the galaxy appears timeless, as though it has always existed exactly as it is now. Yet, every astronomical object has a history, and M87 is no exception. Long before astronomers understood galaxies, before anyone knew the universe contained countless stellar systems beyond the Milky Way, M87 was simply a faint smudge of light. You can imagine standing beneath an 18th century night sky. There are no satellites streaking overhead, no city lights washing out the stars, and no spacecraft sending photographs from distant worlds. The heavens appear deeper than most modern people ever experience. Even so, the object that would become known as Messier 87 reveals little of its true nature. Through early telescopes it looks fuzzy, not dramatic, not spectacular. Just a small patch of unresolved light. The sort of thing many observers might accidentally overlook while searching for something more exciting. That unassuming appearance is part of what makes the story so charming. One of the mainstream historical facts of this period is that in 1781, Charles Messier added M87 to his famous catalogue of nebulae and star clusters. At the time, astronomers did not understand that many of these objects were actually entire galaxies far beyond the Milky Way. As far as anyone knew, M87 might simply be some unusual cloud of stars inside our own galactic system. The universe was still much smaller in humanity's imagination. You float through the centuries, watching generations of observers point increasingly sophisticated instruments toward the same faint glow. Telescopes grow larger, lenses improve, observatories rise atop mountains. Yet M87 stubbornly keeps many of its secrets. Throughout the 19th century, astronomers classify it among the so-called nebulae. The word itself is wonderfully vague. A nebula could mean almost anything fuzzy in the sky. It was essentially astronomy's version of saying, well, there's definitely something over there. Scientific terminology has become more precise since then, thankfully. Otherwise, modern conferences might sound like groups of experts gathering to discuss very interesting blobs. As technology advances, details slowly emerge. M87 appears larger than many similar objects. Its light seems smooth and evenly distributed. Unlike spiral nebulae, it lacks obvious structure. Observers sketch what they see through telescopes, carefully recording subtle features. These drawings become valuable records of scientific progress. You can almost picture an astronomer sitting late into the night beside a lantern, peering through an eyepiece, trying to capture the faint shape of M87 with pencil and paper. No digital cameras, no image processing software, just patience and cold fingers. One quirky tidbit from the history of astronomy involves how difficult it was to determine the true nature of distant nebulae. Some astronomers believed they were nearby gas clouds. Others suspected they might be enormous star systems. For decades, the debate remained unresolved. The uncertainty seems almost unbelievable now. Today, children can pull up detailed images of galaxies on a phone. Back then, even professionals were unsure whether these objects existed inside the Milky Way or far beyond it. The universe still had invisible walls. Then comes one of the greatest revolutions in scientific history. In the early 20th century, astronomers begin gathering evidence that many nebulae are actually separate galaxies. The breakthrough transforms humanity's understanding of the cosmos. Suddenly, the Milky Way is no longer the entire universe. It is merely one galaxy among countless others. Imagine discovering that your hometown is not the whole world, but just one neighborhood in a continent filled with cities. Then imagine learning there are billions of continents. That is roughly the scale of the intellectual shock. As this realization spreads, M87 acquires a new identity. No longer a fuzzy object inside our galaxy, it becomes an entire galaxy in its own right. An immense collection of stars separated from the Milky Way by tens of millions of light years. The distance alone is staggering. The light-entering telescopes left M87 long before modern civilization existed in its current form. Empires rise and fall while those photons travel through intergalactic space. Languages evolve, borders change, entire generations live and die. Meanwhile, the light simply keeps moving, portently, silently. Eventually, it reaches Earth and lands on a telescope mirror. You continue drifting through this historical timeline as observatories become increasingly powerful. Photographic plates replace hand sketches. Astronomers can now capture more detail than the human eye alone. M87 begins revealing hints of its extraordinary character. Its size becomes more apparent. Its brightness suggests enormous numbers of stars. Its location near the center of the Virgo cluster attracts growing attention. Researchers start asking bigger questions. How massive is this galaxy? How did it form? What powers its core? The answers remain elusive, yet clues accumulate. This is often how science works. Not through sudden revelation, but through countless small observations gradually assembling into a coherent picture. Like building a giant puzzle without knowing what image should appear on the box. One piece at a time, one generation at a time. Historians still argue whether the early resistance to the Island universe idea was primarily due to limited data or deeply rooted assumption about humanity's place in the cosmos. The debate remains a fascinating example of how scientific culture can shape interpretation. You can understand why uncertainty persisted. The distances involved are almost absurd. Even today, many people hear 55 million light-years and simply nod politely while their brains quietly refuse to process it. A light-year itself is enormous. 55 million of them stretches comprehension beyond its comfortable limits. As decades pass, M87 becomes a regular target for observation. Radio astronomy emerges. New wavelengths reveal phenomena invisible to optical telescopes. The universe begins speaking in frequencies human eyes cannot detect. And M87 has plenty to say. Something unusual appears associated with its center, a strange structure, a hint of activity, an indication that this galaxy may not be as quiet as it first seemed. At first, the evidence is subtle, easy to overlook, easy to misinterpret, but it refuses to disappear. The central region behaves differently from the surrounding galaxy. Energy seems concentrated there. Astronomers take notice. The calm, fuzzy patch catalogued centuries earlier is beginning to transform into something far more intriguing. Like a seemingly ordinary house that turns out to contain hidden rooms, secret passages, and perhaps an inexplicably large collection of antique spoons. The deeper scientists look, the stranger M87 becomes. For now, however, the galaxy still guards its greatest secret. The object responsible for its astonishing power remains unseen. No telescope can yet reveal it. No photograph can capture it. Only indirect clues point toward its existence. You drift closer to the galaxy's luminous center, watching as the mystery grows stronger with every decade of observation. The soft glow that once seemed so simple now feels layered with hidden meaning. And somewhere within that glow, an invisible giant waits patiently for humanity to notice. The faint mystery that once appeared as little more than a fuzzy patch now fills your view. Messier 87 stretches before you in all its immense grandeur, and the closer you drift, the more obvious it becomes that this is no ordinary galaxy. Even among the giants of the Virgo cluster, M87 commands attention. You float far above its outer regions and begin to appreciate its sheer scale. The Milky Way is already enormous by everyday standards. If every grain of sand on a beach represented a star, you would still struggle to picture the hundreds of billions contained within our galaxy. Yet, M87 may contain several trillion stars. Several trillion. The number is so large that it almost stops functioning as a number and starts behaving like weather. You do not count it. You simply experience it. The galaxy glows with a soft golden hue because many of its stars are old. Massive blue stars burn brightly but live short lives. Over time, galaxies rich in ancient stellar populations tend to take on warmer colors. M87 looks less like a cosmic firework and more like a vast cathedral illuminated by billions upon billions of candles. Unlike the Milky Way, it lacks sweeping spiral arms. No elegant pinwheel shape turns through space. Instead, the stars occupy a giant elliptical structure, moving along countless overlapping paths. From one angle, the galaxy resembles a luminous sphere. From another, it appears slightly stretched. Everywhere you look, stars fill the darkness, yet despite its calm appearance, M87 tells a story of violence. The mainstream historical fact for this section comes from modern observations showing that giant elliptical galaxies like M87 are believed to have formed through repeated mergers of smaller galaxies over billions of years. You can imagine the process. A smaller galaxy drifts too close, gravity takes hold. Stars pass through stars without colliding because the distances between them are so enormous. Gas clouds crash together. Orbits become scrambled. The two galaxies slowly blend into one. Then another arrives, and another and another. Over billions of years, the elegant spiral structures disappear. The resulting system grows larger, rounder, and more massive. M87 may be the product of countless such encounters. In a sense, it is a galactic city built from ancient cosmic neighborhood. As you move deeper into its halo, another astonishing feature emerges: globular clusters. Thousands of them. The Milky Way hosts around 150 known globular clusters. M87, by contrast, possesses many thousands. These clusters are among the oldest structures in the universe. Each one contains hundreds of thousands of stars, packed into a relatively compact volume. From afar, they resemble glittering ornaments scattered around the galaxy. From nearby, they become entire stellar realms unto themselves. Imagine standing on a planet inside one of those clusters. The night sky would be crowded with stars. Not a few thousand visible points, not even tens of thousands. The heavens might blaze with so many neighboring suns that darkness itself becomes difficult to find. Sleep might require very good curtains. You continue drifting among these ancient companions. Some globular clusters orbit M87 at tremendous distances. Others pass closer to the galactic center. Together they form a kind of celestial swarm surrounding the giant galaxy. One quirky tidbit often discussed among astronomers is that M87's collection of globular clusters is so rich that researchers have spent decades studying them individually, almost as if each cluster were a separate little galaxy. When you possess thousands of ancient stellar systems orbiting one galaxy, ordinary definitions begin to feel inadequate. Everything about M87 seems to operate on a larger scale. The galaxy's halo extends far beyond what your eyes first perceive. Faint stars spread outward into regions so vast that defining the exact edge becomes surprisingly difficult. Where does a galaxy truly end? At what point does its influence fade into the surrounding cluster? The question sounds simple. The answer is not. Even today, astronomers continue refining measurements and models. Nature rarely provides neat borders. It prefers gradual transitions. The deeper you look, the more M87 begins to resemble an ecosystem rather than a single object. Stars orbit. Globular clusters wander. Dark matter exerts its invisible pull. Hot gas fills enormous regions of space. Everything interacts through gravity. Everything moves. Everything changes. Just very, very slowly. Human beings often think in years. Galaxies think in billions of years. That difference in perspective can feel almost meditative. A civilization may rise, flourish, and disappear while M87 barely notices. Its stars continue their orbits. Its clusters continue their journeys. Its central mysteries remain largely unchanged. Historians still argue whether the earliest giant elliptical galaxies formed primarily through major mergers or through a more gradual accumulation of smaller systems. New observations continue to refine the debate, but no single explanation answers every question, since science often advances this way. Not through certainty alone, but through carefully managed uncertainty. Every answer opens another door. Every discovery reveals additional mysteries. You drift farther inward. The density of stars increases. The glow grows brighter. Yet something curious becomes apparent. For all its enormous size, M87 is not producing stars at the frantic rate seen in some younger galaxies. Many of its brightest stars are ancient. The galaxy has matured. Its most active period of stellar birth largely belongs to the distant past. If galaxies were people, M87 would be less energetic teenager and more wise elder who has seen everything and no longer feels the need to rush. An elder who also happens to weigh more than most neighboring galaxies combined, and possibly owns thousands of glittering star clusters for decorative purposes. As you move through this immense stellar kingdom, you begin noticing subtle signs of something unusual near the center. The outer regions feel peaceful. The middle regions feel majestic. But the core feels different. Energy seems concentrated there. The brightness subtly changes. Observations collected throughout the 20th century suggest that the heart of M87 is not merely crowded with stars. Something else lurks within. Something capable of influencing the entire galaxy. At first, the clues are indirect. Unusual motions, unexpected emissions, paths that do not fit simple explanations. Nothing dramatic enough to reveal the answer outright, just enough to provoke curiosity. And curiosity, as always, proves difficult for scientists to ignore. You continue approaching the galactic center. The surrounding glow becomes increasingly intense. Stars stream through enormous gravitational pathways. Ancient clusters circle in the distance. The Virgo cluster stretches beyond the horizon. And somewhere ahead, hidden behind layers of light and matter, lies the object that will eventually change astronomy forever. For now, you can only sense its presence indirectly, like hearing distant thunder before seeing the storm. The giant remains concealed. But not for much longer. The first truly strange clue is about to appear. A narrow beam of energy reaching outward from the heart of the galaxy itself. A feature so unexpected that it will leave astronomers puzzled for decades. And once that beam is noticed, Messier 87 will never again seem like a quiet island of stars. The deeper you move toward the center of Messier 87, the more the galaxy's calm appearance begins to feel deceptive. From a great distance, M87 resembles a peaceful golden lantern suspended in darkness. Billions upon billions of stars blend together into a smooth glow. Nothing about its appearance immediately suggests violence, instability, or extraordinary power. Yet appearances can be misleading. A sleeping cat may look harmless until it decides your keyboard belongs exclusively to it. Likewise, M87 has been hiding something remarkable in plain sight. As 20th century astronomy advances, researchers begin noticing an unusual feature extending outward from the galaxy's central region. At first glance, it resembles a narrow streak. A thin beam, a strange line of light emerging from the heart of the galaxy. This structure becomes known as M87's jet, and it quickly develops a reputation as one of the most fascinating phenomena in astronomy. The mainstream historical fact for this section is that the jet of M87 was first observed visually in the early 20th century, becoming one of the earliest known examples of a relativistic jet associated with an active galactic nucleus. That simple observation created enormous scientific interest. Because galaxies are not generally expected to shoot giant beams into space, stars do many things, planets do many things, even galaxies can surprise you. But a galaxy launching a beam thousands of light years into intergalactic space tends to attract attention. You drift closer, the jet becomes easier to see. It emerges from the central region like a cosmic searchlight aimed across the universe. Bright knots appear along its length. Some regions glow more intensely than others. The structure is not perfectly smooth. Instead, it resembles a flowing stream of energy punctuated by brighter features. For decades, astronomers struggle to explain it. What powers the jet? Why is it so narrow? How can a galaxy generate such an enormous structure? The questions multiply faster than the answers. As radio astronomy develops, the mystery deepens. Telescopes operating at wavelengths invisible to human eyes reveal that the jet extends far beyond what optical observations initially suggested. The visible portion is merely part of a much larger phenomenon, like seeing only the tip of a mountain, while most of it remains hidden beneath clouds. The universe often works this way. Every time humanity invents a new way to observe it, nature reveals additional layers of complexity. You continue floating alongside the jet. The scale is difficult to comprehend. This is not a local feature, not a tiny structure near a star. The jet stretches across thousands of light years. Entire stellar systems could fit comfortably inside portions of it. The energy involved is astonishing. Yet, despite decades of study, astronomers initially cannot identify the engine responsible. They know something extraordinary exists at the center of M87. They simply do not know exactly what. One quirky tidbit from the history of this discovery is that some early researchers proposed explanations ranging from unusual stellar activity to exotic electromagnetic processes. Before supermassive black holes became widely accepted, scientists explored many possibilities. In fairness, they were attempting to explain something genuinely unprecedented. When nature presents a giant beam emerging from the center of a galaxy, creativity becomes part of the scientific process. Some ideas survive, others quietly retire. A few become the astronomical equivalent of showing up to a formal dinner wearing roller skates. Interesting, memorable, not necessarily correct. As observations improve, evidence begins pointing toward an extremely compact energy source. The jet appears remarkably focused. Whatever powers it must occupy a relatively small region compared with the enormous galaxy surrounding it. That clue proves important. Large, diffuse processes struggle to create such narrow structures. A concentrated engine seems more likely. Meanwhile, theoretical physics is undergoing its own revolution. Researchers explore the implications of Einstein's theory of general relativity. The concept of black holes, once viewed by some as mathematical curiosities, gradually gains credibility. At first, the idea sounds almost absurd. An object so dense that even light cannot escape? Space warped to such an extreme degree. The concept feels closer to science fiction than everyday reality, yet equations continue pointing in the same direction. Observations increasingly support them, and M87's jet begins looking suspiciously like something a supermassive black hole might produce. You drift nearer to the galactic core. The surrounding stars become densely packed. Light fills every direction, yet the source of the jet remains hidden, not because astronomers lack curiosity, not because telescopes lack power, but because the object itself emits no visible light. A black hole does not shine, its surroundings shine. Matter falling inward heats dramatically. Magnetic fields become twisted and amplified. Particles accelerate to extraordinary speeds. The black hole acts like a cosmic conductor, orchestrating events around it. You never see the conductor directly. You see the orchestra responding. This distinction becomes crucial. For much of the 20th century, scientists gather indirect evidence: the jet, the energy output, the motions of nearby material. Each clue points toward the same conclusion. Something immensely massive occupies the center of M87, something compact, something powerful, something invisible. Historians still argue whether the acceptance of supermassive black holes was driven primarily by observational evidence or by the growing success of theoretical models. The two developments influenced one another in complicated ways, making the story difficult to separate into neat categories. Scientific revolutions rarely follow clean timelines. Evidence accumulates unevenly. Debates continue. Consensus emerges gradually. And throughout this process, M87 remains one of the most important laboratories in the sky. The jet itself becomes increasingly valuable. Researchers study its brightness, its structure, its composition, its motion. Some portions appear to move at astonishing apparent speeds, a consequence of relativistic effects associated with matter traveling near the speed of light. The phenomenon feels almost magical at first encounter. Objects seem to challenge ordinary intuition, but relativity has a habit of doing that. The universe, it turns out, is under no obligation to behave in ways that feel comfortable to human brains. As you travel alongside the jet, you imagine particles racing outward, electrons spiral through magnetic fields, radiation pours into space, energy flows across distances that dwarf entire galaxies, and all of it traces back to a region hidden deep within the core, a region still beyond direct observation. For now, the galaxy around you remains magnificent. Ancient stars glow softly. Globular clusters drift through distant orbits. The Virgo cluster stretches beyond sight, yet your attention keeps returning to the jet. It feels like a signpost, a cosmic arrow pointing towards something extraordinary, something hidden, something waiting. The beam itself is not the destination, it is the clue. A message written across thousands of light years. A message telling humanity that the center of Messier 87 contains one of the most powerful objects in the known universe. Astronomers are beginning to understand that fact. But understanding is not enough. They want proof. They want measurements. They want to know how massive the hidden object truly is. And in the decades ahead, they will begin one of the most ambitious investigations in modern astronomy. The hunt for the invisible monster at the center of M87 has officially begun. The jet of Messier 87s continues to blaze behind you like a luminous trail across the darkness. By now, astronomers have accepted that something extraordinary occupies the galaxy's center. The evidence is becoming too substantial to ignore. A powerful energy source exists there, hidden within a region far smaller than the galaxy itself, yet somehow capable of influencing matter across thousands of light years. The problem is simple. No one can actually see it. You drift closer toward the galactic core. The surrounding stars form a dense golden sea of light. Their combined glow creates an almost perpetual cosmic twilight. Yet, despite all this brightness, the object responsible for M87's immense power remains invisible. This is where astronomy becomes a little like detective work. Unlike detectives in movies, however, astronomers rarely kick down doors or dramatically remove sunglasses. Mostly, they stare at data for very long periods while consuming alarming quantities of coffee. Still, the principle is similar. When you cannot observe the culprit directly, you study the clues it leaves behind. And M87 is leaving clues everywhere. One mainstream historical fact from this era is that by the late 20th century, astronomers had gathered strong evidence that many active galaxies contained supermassive black holes at their centers. M87 became one of the leading candidates due to its energetic jet and unusual central activity. The investigation begins with motion. Gravity influences everything. Stars orbit because of gravity. Galaxies rotate because of gravity. Clusters of galaxies remain bound together because of gravity. If a massive object hides at the center of M87, nearby stars should reveal its presence through their behavior. And they do. Astronomers carefully measure how stars move near the galactic core. The closer they look, the stranger the results become. Stars are traveling at enormous speeds, far faster than expected if only ordinary visible matter occupies the region. The observations suggest that an incredible amount of mass is concentrated within a relatively small volume. Imagine watching leaves whirl around an unseen whirlpool. Even if the water itself were invisible, the motion of the leaves would reveal something powerful lurking beneath. The stars around M87 are those leaves. Gravity is the hidden whirlpool. As measurements improve, confidence grows. The central object must be extraordinarily massive, not a cluster of ordinary stars, not a cloud of gas. Not some collection of dim objects hiding in the shadows. The mass appears too concentrated, too dense, too extreme. The evidence increasingly points toward a supermassive black hole. You continue drifting inward. The galaxy's center now dominates your surroundings. Everywhere you look, stellar orbits intertwine. Ancient suns travel paths established millions of years ago. Some stars move calmly. Others race through space under the influence of powerful gravitational forces. Each orbit contributes another piece to the puzzle. One particularly fascinating aspect of the hunt involves spectroscopy. Scientists separate our light into its component colors, revealing subtle shifts caused by motion. When stars move toward Earth, their light shifts slightly. When they move away, it shifts differently. These tiny changes allow astronomers to calculate velocities with astonishing precision. It is almost like listening to a distant orchestra and determining how fast each musician is moving based solely on changes in pitch. Human ingenuity can be wonderfully strange. Someone looked at starlight and essentially said, "What if we use this to weigh an invisible monster?" And remarkably, it worked. A quirky tidbit, sometimes discussed among researchers, is that before black holes gained widespread acceptance, alternative explanations occasionally included hypothetical clusters of dark objects packed together in extremely small volumes. The trouble was that such arrangements would generally become unstable over cosmic timescales. Nature seemed reluctant to cooperate with those alternatives. Again and again, the data pointed back toward the same conclusion. A black hole fit the observations better, not because scientists wanted it to, because the universe appeared determined to insist upon it. As the decades pass, more sophisticated instruments arrive. Space-based observatories join ground-based telescopes. Computers become increasingly powerful. Data analysis techniques improve dramatically. Each advancement sharpens the picture, and the picture consistently shows an astonishing concentration of mass at the heart of M87. You begin to appreciate the scale involved. This is not merely a large black hole, not even a very large black hole. The object appears to contain billions of times the mass of the Sun. Billions. The word itself feels heavy. If the Sun were represented by a grain of rice, M87's central black hole would outweigh an entire warehouse filled with rice, possibly several warehouses. At this point, comparison starts surrendering. Numbers become their own form of landscape. The galaxy surrounding you serves as further evidence. Jets emerge from the center. Matter behaves unusually. Energy production reaches extraordinary levels. Everything points toward a gravitational engine, operating on a scale almost beyond imagination. Yet one crucial challenge remains. Evidence is not observation. Scientists can infer the black hole's existence. They can estimate its mass. They can model its effects. But they still cannot see it directly. The event horizon, the boundary beyond which nothing escapes, remains hidden. The black hole itself remains concealed behind the limits of technology. For some researchers, this distinction matters enormously. Astronomy has always sought direct observation whenever possible. Indirect evidence can become overwhelmingly convincing, but the dream remains the same. See it, measure it, photograph it. Turn theory into image. At the time, that dream seems impossible. The object is far too distant, far too small in angular size. Even the most powerful conventional telescopes lack the necessary resolution. Trying to photograph the event horizon would be like standing on Earth and attempting to read the date on a coin resting on the moon. The challenge appears absurd, almost laughable. Yet astronomy has a long history of converting absurd goals into reality. Humans once thought other galaxies could never be resolved. Then they were. People once thought planets around other stars would remain forever undiscovered. Then thousands were found. The impossible has a surprisingly short shelf life in science. Historians still argue whether the strongest evidence for early supermassive black holes came from stellar motions, energetic emissions, or theoretical consistency between multiple observations. Each line of evidence played an important role in building scientific consensus. You continue floating through the bright central regions of M87. The stars around you remain unaware of the debate occurring on a small blue planet tens of millions of light years away. They simply orbit. They shine. They obey gravity. And gravity, more than anything else, tells the story here. Every orbit points inward. Every measurement points inward. Every clue points inward, toward an invisible object of unimaginable mass. The hunt is nearing success. Scientists are becoming increasingly confident that the monster exists. But confidence alone is not enough. The next challenge will be even more ambitious, not merely proving the black hole exists, not merely estimating its mass, but understanding the boundary that defines it, the edge beyond which no signal can return, the mysterious frontier known as the event horizon. And once astronomers begin chasing that frontier, they will find themselves confronting one of the deepest questions in modern physics. The invisible giant at the center of Messier 87 no longer feels like a distant possibility. By now, decades of observations have transformed suspicion into near certainty. Astronomers have measured stellar motions, analyzed radiation pouring from the galaxy's core, and studied the immense jet extending into intergalactic space. Every clue points toward the same conclusion. Something unimaginably massive resides at the heart of M87. The question now becomes more precise. How massive? You drift through the brilliant central regions of the galaxy, where countless stars orbit under the influence of gravity. To the casual observer, the scene appears calm. Stars move along their paths. Light fills the darkness. Nothing immediately suggests the presence of an object billions of times more massive than the Sun. Yet gravity leaves fingerprints, and astronomers have become experts at reading them. The mainstream historical fact for this section is that observations made during the late 20th century and early 21st century allowed scientists to estimate the mass of M87's central black hole at several billion times the mass of the Sun, making it one of the largest known black holes in the nearby universe. That estimate did not emerge overnight. It required years of measurements and increasingly sophisticated techniques. You can think of it as an enormous cosmic weighing process. The difficulty, of course, is that the object being weighed cannot be placed on a scale. Astronomers must instead examine its influence on everything around it. Stars become test particles. Gas clouds become indicators. Even light itself becomes evidence. One method involves studying how rapidly stars move near the galactic center. According to gravity, objects orbit faster when they are closer to a massive central body. The stronger the gravitational pull, the greater the orbital speed. By measuring those speeds, researchers can calculate the mass responsible. The mathematics is elegant. The implications are astonishing. Again and again, the numbers point toward billions of solar masses compressed into a surprisingly compact region. The conclusion becomes difficult to escape. You continue drifting inward. Imagine standing in a city square and observing people running around an invisible monument. If everyone is moving unusually fast, you might infer that something important occupies the center. Perhaps a fountain, perhaps a stage, perhaps an extremely popular coffee stand. In M87, the hidden attraction is somewhat larger and significantly more dangerous. As observations improve, astronomers begin measuring not only stars but also gas near the galactic core. Gas behaves differently from stars. It can collide, it can heat up, it can form disks and streams. Those characteristics make it particularly useful for understanding central gravitational forces. When gas moves at extraordinary velocities around an unseen object, researchers gain another powerful tool for estimating mass. The results continue telling the same story. A very large story, a very heavy story, the kind of story that bends space-time. One quirky tidbit associated with these measurements is that some of the earliest black hole mass estimates generated heated debates because the numbers seemed almost absurdly large. Billions of solar masses sounded extravagant even to many astronomers. Nature, however, has never shown much concern for human preferences. If anything, the universe appears to enjoy producing objects that exceed expectations. Black holes with billions of solar masses? Certainly. Galaxies containing trillions of stars? Why not? Cosmic structures stretching across hundreds of millions of light years? Apparently those as well. The universe is not a minimalist designer. As the evidence accumulates, scientists begin refining their models. The estimated mass of M87's central black hole grows increasingly precise. Different methods produce broadly consistent results. Independent observations support one another. Confidence strengthens. You start to appreciate just how extraordinary this object truly is. Suppose the Sun were replaced by M87's black hole. The planets would continue orbiting from a purely gravitational perspective if the mass was somehow unchanged. But M87's black hole is not merely one solar mass. It is billions of times more massive. The scale defies ordinary comparison. Even light requires hours to cross distances that seem tiny compared with its overall influence. Its gravitational reach extends across vast portions of the galaxy. Yet despite its immense mass, the black hole itself remains remarkably compact relative to the system surrounding it. That paradox fascinates scientists. Enormous mass, relatively small volume, extreme gravity, those ingredients create some of the strangest environments in the known universe. You drift near regions where matter spirals inward. Gas becomes compressed. Temperatures rise dramatically. Magnetic fields twist and stretch. Energy is released in quantities that dwarf most stellar processes. The center of M87 resembles a giant natural laboratory where physics operates under conditions impossible to recreate on Earth. Every observation becomes valuable. Every measurement teaches something about gravity. Every improvement in technology reveals new details. Historians still argue whether the most important breakthrough in measuring supermassive black holes came from improved telescope resolution or from advances in computational modeling. The two developments evolved together, making their individual contributions difficult to separate. This is often the case in scientific progress. Instruments improve, theory improves, computers improve. Each advance strengthens the others. Together they push knowledge forward. You continue gazing toward the hidden center. By now, astronomers have become increasingly confident about the black hole's mass. Yet another challenge emerges. Knowing the mass is not the same as observing the event horizon. researchers understand that something extraordinary exists. They understand roughly how large it is, but they still cannot directly image the defining feature of a black hole itself. The event horizon remains frustratingly out of reach. Its apparent size on the sky is incredibly small. Even from a distance of roughly 55 million light-years, the black hole occupies only a tiny angle. Conventional telescopes simply lack the necessary resolving power. It is like trying to see a grain of dust on a distant mountain while standing across an ocean. The challenge seems almost impossible. Almost. Astronomers begin calculating what would be required to image the region around the event horizon. The answer sounds ridiculous. To achieve sufficient resolution, they would effectively need a telescope the size of Earth. Not a large telescope, not a very large telescope, an Earth-sized telescope. At this point, many reasonable people might politely conclude that such a project is unrealistic. The universe, however, appears to reward unreasonable persistence, and astronomers can be remarkably persistent, particularly when confronted with a mystery. The black hole of M87 has already reshaped our understanding of galaxies. Its mass has been estimated, its influence has been mapped, its jet has been studied, yet the ultimate prize remains unattained. No human being has ever seen the shadow of a black hole. No photograph exists. No image confirms what theory predicts. For now, the event horizon remains hidden behind the limits of observation. But those limits are beginning to change. Around the world, scientists are preparing for a project unlike anything attempted before. A project so ambitious that it will connect observatories across continents. A project designed to transform Earth itself into a giant virtual telescope. And if it succeeds, humanity may finally glimpse the edge of the invisible giant waiting at the center of Messier 87. The closer astronomers come to understanding the black hole in Messier 87, the more they encounter a curious problem. They know the object exists. They know it is unimaginably massive. They know it powers a gigantic jet stretching across thousands of light years. Yet the black hole itself remains hidden, not hidden behind dust, not hidden behind distance alone. Hidden by its very nature. A black hole is, in the simplest sense, a place where gravity becomes so powerful that nothing can escape once it passes a certain boundary. That boundary is known as the event horizon, and now your journey slows as you approach one of the strangest ideas in all of physics. The event horizon is not a wall, not a surface, not a cosmic force field. If you were somehow floating nearby, you would not see a glowing line painted across space. The boundary exists because of gravity and geometry. Cross it, and every possible future path leads inward. There are no roads back out, no emergency exits, no helpful signs saying, perhaps reconsider this decision. The universe can be surprisingly direct. The mainstream historical fact for this section is that the modern understanding of black holes emerged from the theory of general relativity developed by Albert Einstein in 1915, though Einstein himself was initially skeptical that such extreme objects would exist in nature. That skepticism seems almost comforting. Even one of history's greatest physicists occasionally looked at an idea and thought, that sounds a bit excessive. Nature responded by creating billions of black holes anyway. You continue drifting through the conceptual landscape surrounding M87's central monster. Unlike planets, stars, or galaxies, black holes challenge ordinary intuition. Everything you learn about them feels slightly wrong at first. Time behaves differently. Space behaves differently. Cause and effect remain intact, but the geometry underlying reality becomes deeply unfamiliar. Imagine standing on a moving walkway at an airport. Now imagine the walkway is accelerating. Then imagine it is accelerating so dramatically that every available path eventually carries you toward a single destination. That image captures only a tiny fraction of what happens near an event horizon. But it helps. Gravity is not merely pulling objects. It is reshaping spacetime itself. As scientists study M87's black hole, they become increasingly interested in what should appear near this boundary. Not the event horizon directly. That remains invisible. Instead, they focus on the surrounding region. Matter falling inward heats to extraordinary temperatures. Magnetic fields twist and interact. Radiation emerges from energetic processes near the edge. In theory, these effects should create a distinctive pattern, a glowing ring surrounding a dark central shadow. The prediction is elegant, the challenge is seeing it. You float closer in imagination. The black hole itself still cannot be observed directly. No light escapes, no image forms. Yet according to relativity, the black hole should cast a kind of silhouette against the glowing material around it, a shadow. Not a shadow in the ordinary sense produced by blocking sunlight, a shadow produced by gravity redirecting light itself. The idea feels almost poetic, an object invisible by nature, revealing its existence through the absence of light. One quirky tidbit connected to black hole research is that some physicists spent decades debating whether information falling into black holes is truly lost forever. This puzzle eventually became one of the most famous unresolved questions in theoretical physics. Black holes, it turns out, are not content with challenging astronomy. They also enjoy provoking philosophers, mathematicians, and anyone else who values a good night's sleep, which is slightly inconvenient for a bedtime story. Fortunately, tonight you are observing from a safe distance, very safe, extremely safe, 55 million light-years safe. The sort of safe distance where even the most enthusiastic black hole cannot realistically inconvenience you. As observations of M87 continue, researchers compare theory with data. General relativity predicts specific behaviors near a black hole. Light should bend, orbits should change, matter should accelerate. The black hole's mass should determine the apparent size of its shadow. Every measurement becomes an opportunity to test the theory. And remarkably, the theory continues passing those tests, again and again, for more than a century. That consistency strengthens confidence, yet scientists remain cautious. They want direct evidence. They want observation rather than inference. They want to compare reality with prediction in unprecedented detail. This desire leads naturally to a difficult question. Can the shadow actually be photographed? At first glance, the answer appears negative. The angular size is tiny, absurdly tiny. From Earth, the shadow occupies a region so small on the sky that conventional telescopes cannot resolve it. Even enormous observatories fall short. The obstacle is not brightness alone. It is resolution, the ability to distinguish extremely fine details. Historians still argue whether the greatest obstacle to imaging a black hole was technological limitation or conceptual skepticism. Some researchers focused on building better instruments, while others questioned whether such observations would ever become feasible. Both perspectives were understandable. The challenge bordered on outrageous. To resolve the shadow directly, astronomers would need a telescope far larger than anything ever constructed, not merely larger by a modest amount. Larger by orders of magnitude, the calculations point toward an extraordinary conclusion: a telescope approximately the size of Earth. You pause for a moment beside the galaxy. Earth itself, not a telescope on Earth, a telescope as large as Earth. The proposal sounds almost mythical, like something dreamed up during a late-night conversation between ambitious scientists and equally ambitious coffee cups. Yet the underlying physics is solid. The larger the effective telescope, the finer the detail it can resolve. If a planet-sized telescope could somehow be created, the shadow of M87's black hole might become visible. Might. That word remains important. Successes is not guaranteed. Countless technical challenges stand in the way. Observatories would need extraordinary precision. Data would need synchronization at levels rarely attempted before. Weather, equipment, timing, and computation would all matter. A single weak link could compromise the effort. Still, the possibility exists. For the first time, imaging the shadow no longer seems entirely impossible, just incredibly difficult, and astronomy has always had a soft spot for incredibly difficult goals. You continue gazing toward the hidden heart of M87. The black hole remains invisible. Its event horizon remains concealed, yet its presence dominates everything around it. Stars respond to its gravity. Jets emerge from its vicinity. Light bends around it. Theory predicts its shadow. The challenge is clear, the target is defined. Now, humanity must build the instrument capable of seeing it, and that instrument will not be found in a single observatory. It will be assembled from mountains, deserts, ice fields, and radio dishes scattered across the globe. The next chapter of the story belongs not only to the black hole, but to an extraordinary collaboration that will attempt something never done before. To turn an entire planet into one giant eye pointed toward the center of Messier 87. The giant virtual telescope is ready. Across Earth, observatories sit quietly beneath the stars, separated by oceans, mountains, deserts, and entire continents. To a casual observer, each facility appears independent, a collection of dishes, antennas, buildings filled with equipment. But now they are about to become something larger, much larger. You drift high above the planet and watch the network awaken. The Event Horizon Telescope is not a single machine. It is a collaboration spread across the globe, united by a shared purpose. Every participating observatory must observe the same target at precisely the right moment. The target, of course, remains the supermassive black hole at the center of Messier 87, 55 million light-years away, waiting. The mainstream historical fact for this section is that the Event Horizon Telescope observations that ultimately produced the first black hole image were conducted during a coordinated observing campaign involving observatories across multiple continents. This coordination sounds straightforward until you examine the details. Every telescope must record data with extraordinary precision. Every observation must be synchronized. Weather conditions matter, instrument performance matters, timing matters, everything matters. Astronomy occasionally resembles an orchestra in which every musician is performing from a different continent while attempting to remain perfectly synchronized. You glide from one observatory to another. In Chile, high-altitude facilities take advantage of dry atmospheric conditions. In Hawaii, instruments stand atop volcanic summits above much of the moisture that interferes with radio observations. At the South Pole, equipment operates in one of the most remote environments on Earth. Each location contributes a vital piece of the puzzle. Remove enough pieces, and the final image becomes impossible. One challenge involves the Earth itself. The planet rotates. That might sound obvious. After all, Earth has been rotating quite reliably for billions of years. Yet, for the Event Horizon Telescope, rotation becomes a useful feature rather than a complication. As Earth turns, the relative positions of observatories change with respect to the target. This movement effectively provides additional observational information. The planet helps build the image. Sometimes nature lends a hand, not often, but occasionally you continue watching as data begins flowing into storage systems. The quantities involved are enormous, not merely large, not merely inconvenient. Enormous. Researchers record so much information that conventional data transfer methods become impractical. Hard drives accumulate mountains of observational records. The black hole is not easy to photograph. It demands receipts, many receipts. One quirky tidbit from the project involves the South Pole Telescope's data. Because Antarctica's extreme isolation limits transportation options, some information must wait months before physical storage devices can be transported and combined with data from other observatories. Imagine conducting one of humanity's most advanced scientific experiments and then patiently waiting for hard drives to arrive from Antarctica. Science is often less glamorous than movies suggest, and somehow more impressive. As the observations proceed, researchers know they are attempting something unprecedented. No one has ever imaged a black hole's shadow. No one has ever directly observed the region immediately surrounding an event horizon at this level of detail. Theoretical predictions exist. Computer simulations exist, but observations remain supreme. Nature always gets the final vote. You drift across research centers where teams monitor equipment and verify performance. Scientists understand that success is not guaranteed. Years of preparation could still end in disappointment. A technical failure at a critical moment could compromise valuable data. Atmospheric conditions could interfere. Unexpected complications could emerge. Such uncertainty is normal in frontier science. Progress often requires accepting risk. Not reckless risk, carefully calculated risk. The kind that pushes knowledge forward. As observations conclude, another enormous challenge begins: data analysis. The raw recordings do not immediately resemble a photograph. Far from it, the information must be processed, calibrated, synchronized, and reconstructed. Specialized algorithms help transform measurements into meaningful images. Researchers spend months and years ensuring that every step is reliable. Extraordinary claims require extraordinary care. Nobody wants to announce the first image of a black hole only to discover they accidentally photographed a software bug. That would create a very uncomfortable conference presentation. The scientific teams, therefore, proceed cautiously. Independent groups analyze data separately. Methods are cross-checked. Results are compared, potential errors are investigated. Confidence builds gradually. Historians still argue whether the greatest intellectual challenge of the project lay in collecting the observations or reconstructing a trustworthy image from the data afterward. Both demanded expertise at the highest level. The distinction matters because astronomy increasingly operates at the intersection of observation and computation. Modern discoveries often emerge not only from telescopes, but also from the sophisticated analysis required to interpret their measurements. You continue drifting through the years of work that follow the observing campaign. Researchers remain patient. The world largely waits unaware. Outside the scientific community, daily life continues. People commute to work. Children attend school. Cities glow at night. Meanwhile, hidden within enormous datasets, the shadow of a black hole may already exist. Waiting to be revealed, the thought carries a certain quiet beauty. A discovery can exist before humanity recognizes it. Reality does not require acknowledgement. The black hole has been there all along. Its shadow has been there all along. The challenge is simply learning how to see it. As confidence in the analysis grows, excitement begins spreading through the scientific community. The reconstructed images show familiar patterns. Force predicted by theory start appearing. The structure resembles what general relativity suggested should exist: a bright ring, a darker center, a silhouette carved by gravity itself. Still, researchers remain careful. Verification continues, tests continue, scrutiny continues. No one wants haste to undermine credibility. Eventually, however, the evidence becomes overwhelming. The image is real. The shadow is visible. The impossible appears to have happened. You turn once more toward distant Messier 87. The giant galaxy remains serene in the Virgo cluster. Its stars continue shining. Its jet continues streaming into space. Its black hole continues shaping the surrounding universe. Yet something fundamental has changed. For the first time in history, humanity is on the verge of seeing it, not merely inferring, not merely calculating, seeing a moment decades in the making. A moment built from observatories, atomic clocks, algorithms, cooperation, persistence, and countless hours of effort. The image itself is almost ready to emerge, and when it does, it will travel around the world in a matter of hours. A glowing ring surrounding darkness, a picture that will become one of the most famous scientific images ever created. The shadow is waiting, the reveal is near. And humanity is about to look directly into the heart of Messier 87. The years of preparation, observation, verification, and analysis finally converge into a single moment. You can almost feel the anticipation spreading across research institutions around the world. For decades, black holes have occupied a peculiar place in human imagination. They are among the most famous objects in science, yet nobody has ever actually seen one. Artists create illustrations, physicists construct models, computer simulations generate predictions, but an image, a genuine image, that has remained beyond reach until now. You drift above Earth as scientists prepare to share the result of one of the most ambitious astronomical projects ever attempted. Behind the scenes, countless researchers have spent years checking and rechecking the data from the Event Horizon Telescope. Independent teams have compared methods. Algorithms have been scrutinized. Every possible source of error has been examined. No one wants to rush history, because if the image is real, it represents something extraordinary, not merely a scientific success, a new way of seeing the universe. The mainstream historical fact for this section is that on April 10, 2019, the Event Horizon Telescope collaboration unveiled the first image of a black hole, revealing the shadow of the supermassive black hole at the center of Messier 87. The announcement travels around the globe almost instantly. News organizations cover the story. Scientists celebrate. students stare at screens. People who have never before followed astronomy suddenly find themselves looking at a blurry orange ring. And strangely enough, that blurry orange ring becomes one of the most important images in modern science. At first glance, the photograph appears simple: a glowing, uneven ring of light surrounding a dark center, no dramatic explosions, no giant glowing skull floating through space, no cosmic fireworks spelling out "Congratulations, humanity." Just a ring, a shadow, and yet the meaning behind it is immense. You drift closer to the image itself. The bright ring is created by superheated material orbiting near the black hole. Gas and plasma race around at extraordinary speeds. Temperatures soar to billions of degrees. Magnetic fields twist and interact. Radiation pours outward. The dark center is the shadow. Not the event horizon itself, but the silhouette produced by the black hole's extreme gravitational influence on surrounding light. For the first time, humanity is directly observing evidence of this phenomenon. The image resembles something predicted by Einstein's theory more than a century earlier. That fact alone feels almost miraculous. Imagine writing equations in 1915 and discovering that future generations use a planet-sized telescope to confirm their predictions near a black hole 55 million light-years away. Physics occasionally feels like a very long conversation across time. You continue examining the famous image. One side appears brighter than the other. This asymmetry is expected. Material moving toward Earth appears brighter because of relativistic effects, while material moving away appears dimmer. Even in this historic photograph, Einstein continues quietly influencing the story. The universe seems remarkably fond of rewarding correct mathematics. One quirky tidbit associated with the image is that some people expected the first black hole photograph to look dramatically sharper, perhaps resembling scenes from science fiction films. Instead, the image appears somewhat fuzzy because astronomers are working at the absolute limits of observational capability. Nature rarely provides high-definition close-ups on demand. The fact that the image exists at all is the astonishing part. Trying to photograph the shadow of M87's black hole is often compared to seeing a donut on the moon from Earth. And yet somehow, humanity managed it. You drift through the days following the announcement. The image spreads across newspapers, websites, classrooms, and television broadcasts. Scientists who devoted years to the project finally see the world reacting to their work. For many researchers, the moment carries deep emotional significance. Some spent decades pursuing the goal. Some helped develop technologies necessary for success. Others contributed theoretical foundations long before the observations became possible. The photograph belongs to all of them. And in a broader sense, it belongs to humanity. It represents what becomes possible when curiosity persists across generations. You return your attention to Messier 87 itself. The galaxy remains distant, ancient, silent, yet now it possesses a new distinction. Its central black hole has become the first ever directly imaged. Not the closest black hole, not necessarily the most famous before the observation, but the first one humanity successfully photographed. That achievement secures M87 a permanent place in scientific history. Historians still argue whether the cultural significance of the image exceeded its scientific significance or vice versa. Some emphasize the technical and theoretical breakthrough, while others focus on its symbolic power as humanity's first visual encounter with a black hole. In truth, both perspectives contain merit. Scientifically, the image provides powerful evidence supporting predictions of general relativity. Technologically, it demonstrates the capabilities of global scientific collaboration. Culturally, it transforms an abstract concept into something visible. People can now look at a black hole's shadow, not imagine it, not read about it. Look at it. There is something profoundly satisfying about that transition. For centuries, black holes occupied the realm of theory, then evidence accumulated, then measurements improved, then confidence grew, and finally an image appeared. The progression feels almost inevitable when viewed in hindsight, yet at every stage, success remained uncertain. The story could easily have unfolded differently. The necessary technology might never have emerged. The observations might have failed. The data might have proved inadequate. Instead, the effort succeeded. The glowing ring became real. You linger beside the image a little longer. The ring seems simple, almost humble, yet behind it stand thousands of scientific papers, decades of research, countless hours of engineering, and generations of curiosity, all condensed into a circle of light surrounding darkness. The photograph answers one question beautifully. Yes, black holes truly behave much as theory predicts, but answers in science have a habit of generating new questions. Now that humanity can see the shadow, researchers want to understand every detail. Why is the ring shaped as it is? How does matter move nearby? What can the image reveal about gravity itself? The famous photograph is not the end of the story. It is the beginning of a new phase. The door has finally opened, and beyond that door lies a deeper understanding of the strange glowing ring surrounding one of the most massive black holes in the nearby universe. The famous image now hangs in your mind like a glowing ember in the darkness, a bright ring surrounding a shadow, simple enough to sketch on a napkin, complex enough to occupy hundreds of scientists for years. You continue drifting beside the black hole at the center of Messier 87, no longer asking whether it can be seen, but what exactly humanity is seeing when it looks at that remarkable image, because despite all the headlines proclaiming the first picture of a black hole, the reality is a little more subtle, and, as is often the case in astronomy, a little stranger. The black hole itself remains invisible. That fact has not changed. It cannot change. No light escapes from within the event horizon. No camera can directly photograph the interior. The image instead reveals the effects of the black hole on the environment around it. You are seeing gravity made visible through light. You are seeing the universe drawing the outline of something that cannot be observed directly. The mainstream historical fact for this section is that the size of the shadow observed by the Event Horizon Telescope closely matched predictions derived from Einstein's theory of general relativity, providing one of the strongest observational tests of black hole physics ever achieved. That agreement delighted physicists, not because they enjoy being proven right, although, like most humans, they generally do, but because nature once again confirmed a theory that had survived more than a century of scrutiny. The shadow appears larger than the actual event horizon itself. This surprises many people when they first learn it. Gravity bends the paths of light traveling near the black hole. Photons that might otherwise escape become redirected. Others become trapped. The resulting distortion enlarges the apparent dark region. In a sense, The black hole creates a gravitational magnifying effect around its own silhouette. The geometry is so unusual that ordinary intuition struggles to keep pace. If space behaved this way in your living room, finding the television remote would become a truly heroic challenge. You drift closer in imagination. Around the black hole swirls an environment of extraordinary violence. Gas spirals inward, magnetic fields twist and reconnect. Temperatures rise to levels difficult to comprehend. Particles race at speeds approaching that of light, yet from millions of light years away, all of that complexity condenses into a glowing ring. There is something almost poetic about it. Chaos at one scale, elegance at another. Astronomy repeatedly teaches this lesson. The universe often appears simpler from a distance than it does up close. The ring itself is not a rigid structure. It is a snapshot, a moment captured during an ongoing process. Matter continues moving. Energy continues flowing. The black hole continues feeding from its surroundings. The image freezes one instant within a constantly evolving system. One quirky tidbit that emerged after the image release is that scientists generated many independent reconstructions before revealing the final result. Separate teams worked without knowing what the others were producing, helping ensure that common features were genuine rather than artifacts of a particular method. This approach resembles asking several artists to sketch the same landscape independently. If all of them produce similar mountains, rivers, and trees, confidence increases that the scene is real. If one artist produces a volcano shaped like a giraffe, additional questions may be necessary. Fortunately for astronomy, the teams reached broadly similar conclusions. The shadow was real. The ring was real. The structure persisted regardless of analytical approach. You continue examining the image. The brighter portion of the ring catches your attention. This asymmetry arises because material orbiting toward Earth appears brighter than material moving away. Relativity once again enters the story. The effect is known as relativistic beaming. Energy becomes concentrated in the direction of motion. As a result, one side shines more intensely. Even the brightness pattern contains information. Every pixel matters. Every detail contributes to understanding conditions near the black hole. Researchers compare observations with computer simulations. Different models predict different appearances. By matching simulations to data, scientists learn about magnetic fields, plasma behavior, and the flow of matter near the event horizon. The image becomes more than a photograph. It becomes a laboratory, a place where theory and observation meet. Historians still argue whether future generations will remember the M87 image primarily as a triumph of observational astronomy or as a milestone in testing general relativity. Both interpretations remain compelling. The distinction may ultimately prove unimportant. Great discoveries often belong to multiple stories simultaneously. The first moon landing belongs to engineering, exploration, politics, and human imagination. The M87 image belongs to physics, astronomy, technology, and curiosity. Its significance extends beyond any single category. You drift beside the shadow once more. The darkness at its center feels almost hypnotic, not frightening, not hostile, simply profound. A region where gravity has asserted itself so completely that ordinary concepts begin to lose meaning. For generations, black holes occupied the boundary between mathematics and reality. Now they occupy photographs. That transition still feels remarkable. Imagine explaining the image to Charles Messier in 1781. You would tell him that the faint fuzzy patch he catalogued contains a black hole billions of times more massive than the Sun. You would explain radio telescopes, atomic clocks, interferometry, and computer reconstruction. Then you would show him the shadow. He might stare at it for a very long time. And honestly, who could blame him? You continue reflecting on the image's deeper implications. The success of the Event Horizon Telescope demonstrates that some of the most difficult observations imaginable can be achieved through persistence and collaboration. The universe did not become easier to observe. Humanity became better at observing it. That distinction matters. Scientific progress often feels like expanding a circle of light within a vast darkness. The darkness remains immense. Yet the illuminated region grows, little by little. Generation by generation, the image of M87's black hole expands that circle considerably. But it does not end the mystery. Far from it, the photograph answers important questions, yet countless others remain. How exactly does the jet form? What role do magnetic fields play? How does matter behave under such extreme conditions? Can future observations reveal even finer details? The shadow has finally appeared. Now scientists want to understand everything surrounding it. And as researchers continue studying the image, they discover that the story of M87's black hole is still unfolding. The first photograph may be historic, but the debates it inspires are only beginning. The shadow of the black hole has finally been revealed. A glowing ring surrounds a dark center. The image travels around the world. Scientists celebrate. Newspapers print it. Students pin it to classroom walls. For a brief moment, a galaxy 55 million light-years away becomes part of everyday conversation. Yet, something interesting happens whenever a major scientific breakthrough occurs. The discovery answers questions, then immediately creates new ones. You continue floating beside the famous image of Messier 87's black hole. At first glance, the result seems definitive. The shadow exists, the ring exists. General relativity appears remarkably accurate. Case closed, except science rarely closes cases quite so neatly. Scientists are professional question askers. Give them a historic image, and many of them respond with excitement, followed almost instantly by, "Interesting. But what does this part mean?" The mainstream historical fact for this section is that after the release of the first black hole image, researchers around the world began conducting extensive follow-up studies, comparing observations with theoretical models and investigating the detailed structure of the ring and surrounding plasma. The debates are not signs of failure. Quite the opposite. They are signs that science is working exactly as intended. Observations generate hypotheses. Hypotheses generate tests. Tests generate new observations. Knowledge advances through this cycle. You drift through conference halls, research institutes, and university offices where astronomers pore over data. Some focus on the brightness distribution around the ring. Others investigate magnetic fields. Still others examine how plasma behaves near the event horizon. Each researcher studies a different piece of the puzzle. Together, they are attempting to understand one of the most extreme environments in the known universe. One major discussion concerns the precise nature of the glowing material surrounding the black hole. The image itself captures radiation produced by energetic plasma. But plasma is complicated, very complicated. It consists of charged particles interacting with magnetic fields under extraordinary conditions. Modeling such behavior accurately is challenging. Nature does not provide instruction manuals. It simply produces phenomena and leaves humanity to figure them out. The black hole, meanwhile, offers no helpful comments, no explanatory diagrams, no customer support hotline, just gravity, lots of gravity. You continue observing the scientific discussions unfold. Researchers compare different simulations. Some models reproduce the observed image particularly well. Others struggle. Each comparison teaches something valuable. Even incorrect models help narrow the range of possibilities. This process resembles solving an enormous cosmic puzzle by systematically eliminating pieces that do not fit. Slowly, the picture sharpens. Another fascinating debate involves the relationship between the black hole and the famous jet extending from M87. Astronomers have known about the jet for over a century. They know it carries tremendous energy. They know it stretches thousands of light years into space. Yet the precise mechanism responsible for launching and sustaining it remains an active area of research. The black hole clearly plays a role. But exactly how? That question remains surprisingly difficult. One quirky tidbit from this period involves how advanced computer simulations began producing visualizations so detailed that some resembled scenes from science fiction films. Despite their cinematic appearance, these simulations are built upon real physical equations describing gravity, magnetism, and plasma dynamics. In other words, the universe occasionally creates images that look as though they belong on a movie poster. Reality can be unexpectedly artistic. As researchers continue examining M87, polarization measurements become particularly important. These observations reveal information about magnetic fields near the black hole. Magnetic fields are invisible, yet their influence shapes the behavior of surrounding matter. They may even help explain how the jet forms and remains so focused over enormous distances. The more scientists learn, the more central magnetism appears to the story. Gravity provides the stage. Magnetic fields help direct the performance. You drift through this growing landscape of discovery. The original image remains iconic, but it no longer stands alone. Additional analyses reveal new layers of information. Paths emerge. Questions evolve. Understanding deepens. The black hole is becoming less mysterious in some ways and more mysterious in others. That apparent contradiction is common in science. The better you understand a subject, the more clearly you recognize its remaining uncertainties. Ignorance often feels simple. Knowledge tends to reveal complexity. Historians still argue whether the greatest legacy of the first black hole image was the confirmation of existing theories or the creation of entirely new research directions. Both outcomes have shaped modern astrophysics in profound ways. The distinction highlights an important truth. Scientific breakthroughs are rarely endpoints. They are launch points. The first photograph of Earth from space did not end exploration. It inspired more. The first detection of gravitational waves did not conclude research. It opened a new observational window. Likewise, the first image of M87's black hole initiates a new era rather than concluding one. You continue floating beside the shadow. Its dark center remains captivating. Its glowing ring remains beautiful. Yet now you see it differently, not as a final answer, as a beginning. Researchers around the world continue testing theories against observations. Some questions concern particle acceleration. Others concern plasma turbulence. Still others explore whether alternative theories of gravity could produce subtle differences detectable in future observations. The debates remain respectful but energetic. Evidence guides the conversation. Data remains the ultimate authority. That commitment to evidence is one of science's greatest strengths. No matter how elegant a theory may appear, nature gets the final vote. And nature has given astronomers an extraordinary new source of information, the black hole itself, or rather, the region immediately surrounding it. As years pass, additional observations accumulate. The Event Horizon Telescope continues improving. Techniques become more sophisticated, computers become more powerful. Researchers learn how to extract even more information from the data. Slowly, the picture evolves. The story is not standing still. Neither, as it turns out, is the black hole's environment. The glowing ring captured in the historic image is only one moment in time. Matter continues flowing. Magnetic fields continue changing. Plasma continues swirling through the region. The system remains dynamic, alive, with motion. And future observations will reveal something remarkable. The shadow that seemed frozen in the famous photograph exists within an environment that is constantly shifting. A black hole may appear timeless, but the space around it is anything but still. The famous image of Messier 87's black hole feels almost permanent in memory. A glowing ring, a dark center. A historic scientific achievement frozen in time, yet nature rarely stays frozen. The universe is not a photograph. It is a process, a continuous unfolding of motion, energy, and change. You continue drifting beside the black hole, watching the region around it with a patience measured not in minutes, but in years. The shadow itself remains, but the glowing material surrounding it refuses to stand still. Gas continues spiraling inward, magnetic fields continue twisting through space. Particles continue racing at extraordinary speeds. The environment around the black hole is alive with activity. And as observational techniques improve, astronomers begin noticing signs of that activity directly. The mainstream historical fact for this section is that follow-up observations by the Event Horizon Telescope revealed changes in the appearance of the bright ring surrounding M87's black hole, demonstrating that the environment near the event horizon evolves over time. This discovery is both expected and exciting. Expected because theory predicts constant motion. Exciting because humanity can now observe that motion for decades. Scientists could only infer what happened near a black hole. Now they can watch it, not like a movie, at least not yet, but enough to detect genuine changes. Enough to confirm that the region is dynamic. You float above the swirling plasma. The material orbiting near the black hole behaves unlike anything encountered in ordinary life. Temperatures reach extraordinary levels. Magnetic fields become tangled and stretched. Radiation bursts through space. Matter circles at substantial fractions of the speed of light. Everything is in motion. Everything is interacting. Everything is changing. The famous image from 2019 captured one instant within that ongoing dance. Later observations reveal that the brighter regions around the ring shift position. Poles evolve. Structures rearrange themselves. The black hole's surroundings are not fixed architecture. They resemble weather, cosmic weather, the sort of weather forecast that begins with, "Today, magnetic turbulence near an event horizon." You would need a very unusual umbrella. One fascinating aspect of these observations is that the black hole itself remains remarkably stable, while its surroundings remain highly variable. This distinction matters. The shadow is determined primarily by the black hole's mass and gravity. Those properties change very slowly. The glowing plasma, however, responds to local conditions. It churns, flows, reorganizes. The contrast creates a beautiful image, an enduring darkness surrounded by restless light. You continue watching matter circle the black hole. The velocities involved are astonishing. Some particles complete orbits in surprisingly short periods compared with the immense scales involved. The environment behaves more like a storm than a static structure. Astronomers compare observations collected at different times. Pores emerge, doze improve, understanding deepens. The black hole is no longer merely an object. It becomes a system, a complex interaction between gravity, magnetism, radiation, and matter. One quirky tidbit associated with these studies is that some researchers describe the plasma near black holes using terminology that sounds remarkably similar to discussions of fluid dynamics on Earth. Concepts like turbulence, flow, and instability appear in environments separated by 55 million light-years and billions of degrees. The universe enjoys reusing successful ideas. A storm cloud and a black hole's accretion flow are obviously very different. Yet certain physical principles appear in both. Nature loves patterns. As observations accumulate, attention increasingly turns toward the jet. The giant beam extending from M87 remains one of the most spectacular structures associated with the galaxy. Researchers hope that improved understanding of the black hole's immediate surroundings will clarify how the jet forms. Magnetic fields appear especially important. Many models suggest that spinning black holes and magnetic field interactions help channel energy outward. The details remain under investigation. But the evidence continues pointing toward an intimate connection between the black hole and its colossal jet. You drift outward briefly and look along the beam. Thousands of light-years stretch before you. Particles stream through space. Radiation pours outward. Energy travels across distances that dwarf entire galaxies. And all of it may ultimately trace back to processes occurring near the event horizon. The scale contrast is remarkable. Tiny changes near the black hole influence structures extending across intergalactic space. A relatively small region shapes an enormous cosmic environment. Historians still argue whether future observations will reveal subtle deviations from current models of black hole behavior, or continue strengthening the framework established by general relativity. The debate remains open because science always leaves room for surprises. That possibility keeps researchers interested. General relativity has passed every major test for more than a century. Its success is extraordinary. Yet scientists remain eager to probe deeper, not because they expect failure, because every successful test teaches something new. And occasionally, nature reveals an unexpected detail. You continue floating beside the evolving ring. The changing brightness patterns feel almost alive. Not alive in a biological sense, of course. The black hole is not thinking, not planning, not composing dramatic speeches about gravity. It is simply following physical laws. Yet those laws create complexity rich enough to resemble living systems at times. Ports emerge, patterns shift, structures evolve. The universe continuously writes and rewrites itself. The more astronomers observe M87, the more they appreciate that the first image represented only a beginning. The black hole is not a static target. It is a dynamic laboratory. Future observations promise sharper images, more detailed polarization measurements, better understanding of magnetic fields, perhaps even moving sequences showing how the plasma evolves over time. The possibilities continue expanding. You gaze once more into the shadow. The darkness remains profound. The surrounding light continues flowing. Gravity bends space-time exactly as Einstein predicted. Yet every new observation adds nuance to the story. The black hole is no longer merely a theoretical object, no longer merely a photograph. It has become an observed, evolving environment, a place where some of the most extreme physics in the universe unfolds before humanity's instruments. And the lessons emerging from that environment extend far beyond a single galaxy. Because what astronomers learn here helps illuminate black holes everywhere. From the largest giants to the smallest stellar remnants, Messier 87 has become more than an object of study. It has become a cosmic classroom, and its most important lessons are still ahead. The changing ring around the black hole gradually fades behind you as your attention broadens once more. For many years, Messier 87 was simply one remarkable galaxy among countless others. Then it became the home of an extraordinary jet. Later, it became one of the strongest candidates for hosting a supermassive black hole. Eventually, it became the site of humanity's first direct image of a black hole's shadow. Yet perhaps the most important part of the story is not what M87 teaches us about itself. It is what M87 teaches us about the universe. You drift outward from the galactic center. The glowing ring becomes smaller. The immense elliptical galaxy expands into view again. Ancient stars fill the darkness. Thousands of globular clusters orbit through the halo. The famous jet stretches far into intergalactic space. Everything about M87 feels enormous. And because it is so extreme, it serves as a natural laboratory for studying fundamental physics. The mainstream historical fact for this section is that observations of M87 have played a major role in testing predictions of general relativity, particularly in the strong gravity environments surrounding supermassive black holes. This achievement cannot be overstated. Most of the gravitational effects humans experience are relatively mild. You drop a spoon. Gravity pulls it downward. You jump. Gravity pulls you back. Youthful, reliable. Not particularly dramatic. Near a supermassive black hole, however, gravity enters an entirely different regime. Space bends significantly. Time behaves differently. Light follows curved paths. The universe begins acting in ways that seem almost impossible from an everyday perspective. And yet, Einstein's equations continue describing those behaviors with remarkable accuracy. M87 provides one of the most demanding testing grounds ever examined. The fact that theory and observation agree so closely remains one of the great triumphs of modern physics. You continue drifting through the galaxy. The stars surrounding you appear calm, yet M87 also teaches important lessons about galaxy evolution. Astronomers increasingly suspect that supermassive black holes are not merely passengers inside galaxies. They may actively influence how galaxies develop over billions of years. This idea surprises many people. After all, black holes occupy tiny regions compared with entire galaxies. How can something so compact affect structures containing trillions of stars? The answer lies in energy, specifically extraordinary amounts of it. When matter falls toward a supermassive black hole, enormous energy can be released. Jets form. Radiation pours outward. Gas is heated and redistributed. These processes can influence star formation across vast distances. In a sense, the black hole and the galaxy participate in a long cosmic conversation. Neither evolves completely independently. One quirky tidbit sometimes mentioned by researchers is that certain simulations suggest supermassive black holes may help prevent giant galaxies from producing too many new stars. By heating surrounding gas, they can limit the availability of material needed for stellar birth. The idea feels almost parental. The black hole sitting at the center of the galaxy saying, "No, I think that's enough stars for now." The galaxy may not appreciate the advice. Gravity, however, tends to have the final word. You look again toward the jet. It remains one of M87's most impressive features. Extending thousands of light years, it demonstrates how energy generated near a black hole can influence regions vastly larger than the event horizon itself. The jet helps transport energy into the surrounding environment. It affects intergalactic gas. It contributes to the larger ecosystem of the Virgo cluster. This realization changes how astronomers think about galaxies. Galaxies are not isolated islands. They interact with their surroundings. They exchange energy. They participate in larger cosmic structures. M87 illustrates these connections beautifully. You drift farther outward, the Virgo cluster spreads around you. Hundreds and hundreds of galaxies populate the region. Some are spirals. Some are ellipticals. Some are actively forming stars. Others appear relatively quiet. Yet all of them exist within a larger gravitational framework. Dark matter shapes their motions. Gravity binds them together. And giant galaxies like M87 play important roles within that architecture. The lessons extend even further. Black holes similar to the one in M87 likely exist throughout the universe. Many galaxies appear to host supermassive black holes at their centers. The Milky Way itself contains one. Smaller than M87's giant, certainly, but still extraordinary. By studying M87, astronomers gain insights applicable across cosmic history. The galaxy becomes a reference point, a benchmark, a place where theories can be tested against reality. Historians still argue whether future generations will view the first black hole image as the defining achievement of M87 research, or merely the opening chapter of a much larger scientific story. The answer may depend on discoveries that have not yet been made. That possibility is exciting. Science never truly reaches a finish line. Every generation inherits unanswered questions from the one before, then adds new questions of its own. M87 exemplifies this process. Charles Messier catalogued a fuzzy patch of light. Later astronomers recognized a giant galaxy. Subsequent researchers discovered a jet. Then evidence for a supermassive black hole emerged. Then the black hole was imaged. Each generation expanded the story. Each generation saw farther. You continue drifting through the galaxy's outer halo. The stars grow more sparse. The darkness deepens. Yet the significance of M87 feels larger than ever. It represents humanity's ability to understand phenomena far removed from everyday experience. No one will ever visit M87, at least not within any timescale recognizable to civilization. The distances are simply too great. Yet understanding does not require travel. Through observation, mathematics, and collaboration, humanity has learned to explore places it may never physically reach. That achievement deserves appreciation. A species confined to one small planet has managed to investigate a black hole 55 million light-years away. Not perfectly, not completely, but meaningfully. You take one final look toward the center. The invisible giant remains there. Its shadow continues shaping surrounding light. Its gravity continues guiding matter. Its jet continues reaching across space, and its lessons continue influencing modern astronomy. The galaxy that once appeared as a faint smudge in a telescope has become one of the most important objects in the history of science. Yet, as impressive as that journey has been, one final reflection remains, a quieter reflection, a slower one, the kind that arrives near the end of a long voyage through deep time and deep space. Soon, the details will begin to soften, the pace will slow, and the immense story of Messier 87 will settle gently into perspective beneath the stars. The vastness of Messier 87 now stretches quietly around you, after everything you have seen. The ancient stars, the immense halo of globular clusters, the colossal jet, the invisible giant at the center, and the historic image that changed astronomy forever. The galaxy feels strangely familiar, not small, never small, but familiar. Like a distant mountain range that seemed mysterious when first glimpsed on the horizon and gradually revealed its shape as you approached. You drift slowly through the outer regions of the galaxies. The brilliant core is now far behind you. The famous black hole remains hidden within its shadow. The jet extends into darkness like a silent beacon, and yet everything feels calmer than before, perhaps because understanding has replaced some of the mystery, not all of it. The universe is far too large for that, but enough to appreciate what has been accomplished. The mainstream historical fact for this final section is that Messier 87 remains one of the most intensively studied galaxies in astronomy, continuing to serve as a key target for observations aimed at understanding black holes, galaxy evolution, and extreme physics. The story, in other words, is still being written. Future telescopes will observe M87 with greater precision. Future scientists will ask new questions. Future discoveries will almost certainly reveal details no one currently expects. That has been the pattern from the beginning. Charles Messier saw a faint blur. Later generations saw a giant galaxy, then a jet, then a black hole, then a shadow. The universe rewards patience, sometimes on timescales that span centuries. You continue floating through the darkness. Stars drift past like distant lanterns. The glow of the galaxy softens around you. The Virgo cluster stretches beyond sight. Other galaxies shimmer far away, each carrying stories of its own. Some contain supermassive black holes. Some may host planets. Some may harbor mysteries yet to be imagined. The cosmos remains wonderfully unfinished. One quirky tidbit often mentioned by astronomers is that if humanity's entire recorded history were compressed into a single second, the light currently reaching Earth from M87 would have begun its journey many thousands of human history seconds ago. The comparison is imperfect, yet it captures something important. The universe operates on scales that dwarf ordinary experience. And still, somehow, human curiosity reaches across those scales. That may be the most remarkable part of the story, not the black hole, not the jet, not even the image, but the fact that a species living on a small, rocky world learned enough physics, engineering, mathematics, and cooperation to investigate an object 55 million light-years away. You pause for a moment and simply observe. The galaxy glows. Gravity quietly shapes every orbit. Ancient stars continue their journeys. Nothing hurries, nothing rushes. Everything unfolds according to rhythms measured in millions and billions of years. Historians still argue whether the greatest scientific revolutions arise from technological breakthroughs or from new ways of thinking. Looking at Messier 87, it becomes difficult to separate the two. Better ideas led to better instruments. Better instruments led to better ideas. Together they opened a new window on reality. You watch the giant galaxy recede into the distance. The famous black hole can no longer be distinguished from the surrounding light. Its shadow disappears into the brilliance of the core. Its presence remains. Its influence remains. But the details begin to blur. The journey is nearing its end. And now, as promised, it is time to let the pace slow even further, to let the immense scales soften, to let the cosmos settle into stillness. The galaxy drifts quietly behind you now. Its golden light grows gentler with distance, fading into the vast tapestry of the Virgo cluster. The stars no longer seem like separate points. Instead, they blend into a soft glow, like embers resting at the edge of a fire long after the flames have settled. Far away, the black hole remains where it has always been. Silent, unconcerned with calendars, clocks, or deadlines, its gravity continues shaping the space around it, just as it did before the first human looked upward and wondered what lay beyond the night sky. And perhaps there is something comforting in that. The universe is unimaginably large. Its distances are vast. Its timescales are immense. Yet tonight, for a little while, you crossed those distances in imagination. You wandered among ancient stars. You followed a jet of energy through intergalactic space. You stood beside the shadow of a black hole, and now, gently, you leave it behind. The galaxies become softer, the darkness becomes calmer. The questions that remain unanswered can stay unanswered until another night. There is no need to solve every mystery before sleep arrives. The stars will still be there tomorrow. Messier 87 will still be shining in the Virgo cluster. Its black hole will still be quietly bending space-time. The universe is in no hurry. So let your thoughts drift as slowly as those ancient stars. Let the vastness become peaceful rather than overwhelming. Let the darkness feel gentle. And as the distant glow of that giant galaxy fades into the background of the cosmos, allow yourself to settle into stillness, carried by the quiet rhythm of space itself.